Hi everyone, Dr. Burns here with your first lesson in Chapter 4, where we're going to be talking about the development of the periodic table, electron configurations, and how we use those with our modern periodic table. So to begin, let's talk about how that periodic table that we've been using so far this semester, let's talk about how it was developed. Well, in 1864, John Newlands noted that when the elements were arranged in the order of atomic number, every eighth element had similar properties, and he referred to this as the law of octaves. Octaves meaning 8. We're going to find through our lessons in this chapter and in future chapters that 8 is great. 8 is a very important number. So then, in 1869, Dmitri Mendeleev and Lothar Meyer independently proposed the idea of periodicity, meaning that things repeat. Okay, something is periodic, it's repetitive. That's what periodicity means. It means repetitive. Mendeleev was able to group all of the known elements at the time according to their properties, and was even able to predict properties for elements that were not yet discovered, such as gallium, Ga. What Mendeleev could not explain were inconsistencies, such as why argon comes before potassium in the periodic table, even though it has a higher atomic mass. So what I want you to do is actually view that on your own periodic table. Pull your periodic table out, and I want you to look at the mass of argon and potassium, so elements number 18 and 19, and you'll notice that argon has a higher mass than potassium, 39.95 for argon, whereas potassium is 39.10. In 1913, Henry Moseley discovered the correlation between the number of protons, which is the atomic number, which is how they had the periodic table organized, okay, and the frequency of X-rays that each element generated. Now, while we're not going to go into depth about what X-rays are and how they're generated, that's just how they figured it out back then when they didn't know much about elements in general. So they decided that ordering the periodic table by atomic number instead of atomic mass enabled scientists to make sense of any discrepancies. So with argon and potassium, argon acted a lot like the other elements in its column, such as neon, helium, krypton, in that it was a gas and it wasn't very reactive. So what we look at today on our periodic table is organized by atomic number and symbol, and they're specifically arranged according to their electron configuration. So how many electrons it has and how those electrons are organized. And that's what we're going to learn about in our lecture today. So the big kind of conclusion of the development of the periodic table is that elements in the same column have similar properties, which is why we give many of those columns specific names, which we've talked about in a previous lesson in a previous chapter. So if we look at one element, we can assume that any elements above and below it in its group would have similar properties. So let's do a few practice problems here. Pull out your periodic tables and think about what elements would you expect to have similar properties to chlorine. Well, we said previously that argon acted a lot like neon, helium, krypton, and xenon, so chlorine will most likely be like fluorine, F, bromine, Br, and iodine, as well as that last element on our periodic table, which I can never pronounce, so I'm not even going to try. So fluorine, bromine, and iodine are all halogens, as is chlorine, and they're all found in group 7A or group 17. So they would all have similar properties. What elements would you expect to have similar properties to silicon? There's a typo there, silicon. Okay, so silicon is in group 4A or group 14. It's number 14, element number 14. And it is in the same group as carbon, germanium, tin, and lead. So we would expect those elements to have similar properties. Carbon, germanium, tin, which is Sn, and lead, Pb. Now, as we go down that column, we start to go into our metalloids and our metals. So while they may not be exactly the same, they are very similar in some of their properties. But we do have to remember that the big designation between all of our elements is whether they are metals, nonmetals, or metalloids. That's going to be our first distinction before we talk about their properties within their same group. So you have to remember that as well. Finally, what elements would you expect to have similar properties to magnesium? Where is magnesium on our periodic table? Well, it's in group 2. Okay, group 2 on the left-hand side of our periodic table. It's element number 12. So if we look in its column, we would expect it to have similar properties to beryllium, calcium, strontium, and barium, as well as radium. Okay, so elements in the same group have similar properties. Okay, so let's talk about these electron configurations and how we're organizing electrons in our periodic table. So generally, an electron configuration describes how electrons are distributed in the various atomic orbitals. Now, before we go into specifically electron configurations, I want to take a slight sidetrack to talking about what an atomic orbital is. There was a lot more description of atomic orbitals back in chapter 3, which we did not cover, just because some of it is just not relevant to what we're doing in this course. So some of this that we're going to be talking about is coming from chapter 3, so if you'd like to read through this on your own, you're more than welcome to do that in your own textbook. But what I'm going to give you here about atomic orbitals is a nice overview so that we understand the organization that comes along with electron configurations. So, an atomic orbital is where electrons are housed in the atom. It is a three-dimensional description of the location of an electron around an atom. Now we have to remember that electrons are going around our nucleus. Okay, they're three-dimensional. It's not, we used to draw our atoms like this, where it had these layers, kind of like an onion. But we have to remember that this is in 3 dimensions. So there's really, one's going this way, and I'm not good at drawing in 3D, going that way. So we have to remember that this is all 3-dimensional, and the atomic orbitals are going to help us describe the location of those electrons in 3 dimensions. So there are 4 types of atomic orbitals that we are going to utilize and talk about. That is the s orbital, the p orbital, the d orbital, and the f orbital. So we want to remember these 4 orbitals, s, p, d, and f. Those are the 4 types of atomic orbitals where we could find electrons. So, atomic orbitals are 3-dimensional shapes, and each type of orbital has a different shape, and what we're going to refer to as an orientation in space, because it's 3-dimensional, so they have to think about their orientation in a 3-dimensional world. So, to start us off, the s orbital. The s orbital only has one possible orientation in space because it looks like a sphere. So that's this image here. This is an s orbital. It is a sphere. And one s orbital holds 2 electrons. So we can fit an electron in 2 electrons in one s orbital. The p orbital has 3 possible orientations in space. Okay, so 3 possible orientations, and that's going to be in our 3 planes, our x, y, and z 3-dimensional plane. Now, p orbitals have a dumbbell shape or a figure 8 shape, so that's this image over here. P orbitals are over here, okay, and they look like dumbbells or figure 8s. And there's 3 orientations. and that is the p sub x, meaning it lies along the x-axis. So there's our x-axis, and the p orbital lies along that one. We have our y or p sub y orbital, which lies along our y-axis, and our p sub z orbital, which lies along our z-axis. So each orbital is in one dimension of our three-dimensional space. For electrons, each p orbital holds 2 electrons. So each p orbital can hold 2 electrons. So maybe now you're seeing the pattern that with each orbital orientation, it holds 2 electrons. So overall, all three orientations of the p orbital can hold a maximum of 6 electrons. Okay. The d orbital has 5 possible orientations in space, and these ones look generally like flowers. We don't need to remember their specific names, so the specific orientation, such as, dx squared minus y squared or anything like that. We just have to remember that there are 5 orientations in space. And just like our previous orbitals, each orientation can hold 2 electrons. Can hold 2 electrons in each of these orientations, meaning in total the maximum amount of electrons is 10 electrons. So the d orbital can hold a maximum of 10 electrons because each orientation holds 2 electrons, and there are 5 orientations of the d orbitals. The f orbitals are far more complex in their shape, that you don't need to concern yourselves with them, but there would be 7 orientations of f orbitals. So of the very complex shapes that they make, there are 7 different orientations of them, meaning they can all hold a maximum of 14 electrons. Okay, so each orientation again holds 2 electrons, and because there are 7 orientations in space of the f orbitals, the maximum amount of electrons that the f orbitals can hold is 14 electrons. Okay, now in our previous chapter we talked about energy levels, electrons moving between energy levels. So our orbitals are going to be dependent on those specific energy levels. Specifically, each new energy level n comes with a new orbital group that is introduced, because as we're moving further and further away from the nucleus, we have more room. That orbit, if you can think about it that way, has a larger radius, so we can fit more and more electrons. So if this is my nucleus here, I'm going to have my first orbit, my second orbit, my third orbit. Okay, I'm drawing it in half, but because it's getting larger and larger, I can fit more and more electrons. Okay, because the electrons, they aren't changing in size, but the orbits are. They're becoming larger, so we can fit more electrons. So we see here by this energy diagram that with each new energy level, so here's n equals 1, n equals 2, and n equals 3, we start off in n equals 1 with just a 1s orbital. So the 1 here tells us that that's n, and then the s is the type of orbital. Then when we go up to n equals 2, we now have a 2s orbital as well as our two p orbitals, remembering that there's 3 orientations of a p orbital in space, so we have to account for all 3 of those here. And you can see those orbital shapes on the other side. Then when we go up to n equals 3, that's when we introduce our d orbitals. Okay, because now there's even more room that we can fit all 5 of those orientations in space because we need to accommodate more electrons. And it's really important to remember that each orientation holds 2 electrons. So I'm going to write this in red. Here we're going to have 2 electrons. But then when we go up to n equals 2, I now have 2 electrons in 1, 2, 3, 4 orientations, so that would be a maximum of 8 electrons in n equals 2. Then when I go up to 3, again I have 2 electrons that are going to fit into the 3s, 3p, and then into the d, as well as there. So we have 10 electrons that can fit in the d, 6 electrons that can fit in the p, so that's a total of 16, and 2 electrons that can fit in the s. So our max here is now 18 electrons. So with each new n, I can accommodate more and more electrons because as we're moving away from the nucleus, our orbits become larger and we can fit more electrons. Okay, so now that we understand what we mean by atomic orbitals and how we can house electrons in them, they have to sit somewhere, the electrons have to go somewhere, and they're sitting in those atomic orbitals, we can now show our shorthand of that through an electron configuration. So again, the electron configuration describes how the electrons are distributed in the various atomic orbitals. In a ground state hydrogen atom, remembering that ground state means that the electron is in n equals 1 from our previous chapter. In a ground state hydrogen atom, the electron is found in the 1s orbital. There's only 1 electron in hydrogen. Remember, if you look in your periodic table, hydrogen is number 1. So it has 1 proton, one electron. And with electron configurations, we only care about the electrons. So the electron is found in the 1s orbital, 1 meaning n equals 1, and s meaning we can fit 2 electrons maximum. But since I only have 1 electron, we can show it looking like this. So what I have here, oops, I want this in blank, is a version of an orbital diagram. Where we show each orbital as a box. I should say each orbital orientation as a box. Because when we get up to the p, we have 3 orientations, meaning we can fit 2 electrons into each of those boxes. So when we talk about orbital diagrams, this is what we're talking about, the box diagrams. So our 1 electron for hydrogen is in the 1s orbital. So we see it here as 1 arrow. So we denote electrons as arrows, specifically half arrows that can be pointed up or pointed down. Okay, and we use this to denote the spin of our electrons. So if we think about it, if I have an orbital, okay, and I can fit 2 electrons in them, these electrons are negatively charged, meaning that they don't like each other. Remember, opposites attract, but similars repel. So what's going to happen is these electrons are going to start to spin in opposite directions because they don't want to be near each other. Okay, so as they start to spin, they're going to spin in opposite directions. So we denote that spin using our arrows. Okay, so we have an up spin and a down spin, meaning they're spinning oppositely. So we can now write a shorthand for this to show where that 1 electron is in hydrogen, and that is what is being shown right here. So we show 1, this is our n value, so that's our principal n value. The s is the type of orbital. And the superscript here is telling you how many electrons are in that orbital. Okay, how many electrons are in that specific orbital. So this overall notation, this 1s1, that is called the electron configuration. So when we're talking about electron configurations, we're going to be seeing 1s, 2s, 2p. We're going to be seeing that type of notation, which we're going to walk through here. So what happens if we excite that electron? So we talked about, if we put in extra energy, the electrons can move to a higher energy level. Okay, so if we're in an excited state where we have extra energy, the electron is going to move to an orbital of higher energy. So we're going to move, we started off in the 1s, and we're going to move that electron up to a higher energy orbital. Okay, remember, further away, those are higher in energy. That's what we talked about in our previous chapter, in chapter 3. So if we move this electron to a higher energy level, to an excited state, our electron configuration is going to change because our energy level has changed. So now instead of being 1s1, we're now 2s1. So our n value is now equal to 2, which corresponds to where it went to. It's still in an s orbital and there's still only one electron. We just changed energy levels. Now let's say that electron actually went to the 2p. We could write this as 2p1. It's now in the 2p orbital, so energy level 2. It's in a p orbital, and there's one electron still. Now, because there are 3 orientations of the p orbital, we can't tell exactly which one it is, so we don't show any notation like x, y, or z. We can just show it as 2p1, and we know that it's in one of the 3 orientations of our p orbitals. Okay, now one electron is nice and easy because there's only one of them. They don't interact with anything. There's no other electron for it to interact with. But obviously the remainder of our periodic table has more than one electron. So we have to generalize our idea of our electron configuration to the remainder of the periodic table, where we have multi-electron atoms, so more than one electron. More than one electron atoms. So what happens here is our orbitals start to split. So what we saw before was all of these were on the same energy level right next to each other. But now when we're trying to accommodate more than one electron, in order for these orbitals to be energetically favorable, they have to split. Okay, this is going to become important when we start writing electron configurations for larger atoms, which may get a little confusing. So you just have to remember that these trends that we're going to see come out of this splitting. Specifically, we start to see splitting get confusing in this region, where we go from 3s to 3p, but then all of a sudden this 4s comes down in energy and the 3d comes up in energy. And that's because it takes the 3d, since there's 5 orientations, there's a lot more energy in those orbitals in comparison to this one orientation orbital. So the 4s is just more energetically favorable than the 5 orientations of the 3d. And we see that throughout the entire periodic table. Okay, now when we do start to introduce more electrons, we have to follow specific rules about how we're showing those electrons, where we're showing those electrons going. They don't just go into any orbital in the entire atom. They go into specific orbitals and they orient themselves in very specific ways. So the rules that we're going to discuss are very specific to how we are going to build up these orbital diagrams in our electron configurations. So the first rule is the Pauli exclusion principle. And this states that no 2 electrons in one atomic orbital can have the same spin, as we would not be able to tell them apart. So in order to tell electrons apart when they're in the same box, in the same orbital, so remember when we're talking about orbitals, we're talking about one individual box. In order to tell those two electrons apart, they have to be spinning opposite from each other. Remember, because they repel each other because they have the same charge. So here I have hydrogen. And then let's say we move on to helium, where we add one more electron. So we're going to add that electron first to the 1s, because that's our lowest energy. We always want to go from low to high energy. So our electron is going to add to the 1s, but we're going to show it having a downspin. So we started with an upspin over here, and now those two electrons are going to have an upspin and a downspin, because when they're in the same box, they can't have the same spin. So when we show them in an orbital diagram, we show them with two opposite half arrows. Okay, we do the half arrows to show the electrons, okay, and we show them as up and down half arrows. So that's the Pauli exclusion principle. No two electrons can have the same spin so that we can tell them apart. Okay, now what happens if I want to add another electron? So we'll go on to lithium, add 3 electrons. Well, we then follow the Aufbau principle, which states that electrons are added to the lowest energy orbitals first before moving to higher energy orbitals. So when we started with helium, we were in the 1s, and now if I wanted to add one more electron, again, like I said earlier, they don't just go into random orbitals. So it's not like I could just put an electron there and say, yep, that's lithium. That is not true. So the next electron would go into the 2s, because 2s is our next highest energy orbital. Okay, so we fill from lowest energy to highest energy. Okay, so we're going to put that extra electron, or that next electron, in the 2s orbital. Now, continuing on with the Aufbau principle, here we have lithium. We just looked at this one. Then we have beryllium next up. And when we add that one electron, we're following, again, the Pauli exclusion principle, where that electron is going to be added to the 2s, but now have a downspin. Okay, so I had an upspin here. I now have an up and a downspin because two electrons in the same orbital cannot have the same spin, so we can tell them apart. Okay, so I add one more electron to go to beryllium, and I follow my Pauli exclusion principle. Then when I go from beryllium to boron, okay, so now I have 5 electrons that I'm dealing with. I'm adding in one more electron. Okay, that electron now is going to go into the 2p. Okay, because the 2s is full, can only hold 2 electrons. Now I'm going to go to the 2p because that's our next highest energy orbital. So that electron from boron is going to be in the 2p orbital, and typically just the shorthand of it is we show it in the first box first, so we fill up our first orientation before we move on to the next orientation. Okay, so we typically show it in the first box. Now to make a note about our electron configurations, which are down here on the bottom, okay, so we have our orbital diagrams on the top and our electron configurations on the bottom. So here are our orbital diagrams. And here are electron configurations. Okay, we see that with each new electron, we're still keeping the previous orbitals in our electron configuration because our electron configuration has to show where all of the electrons are. So lithium has 3 electrons, 2 of them are in the 1s orbital, and 1 of them is in the 2s orbital, which is what we see in the orbital diagram. Then when we add one more electron to go to beryllium, we now see that we went from 1s2, 2s1 to 1s2, 2s2, because now I have 4 electrons. So our superscripts here, if we add them up, they equal our number of electrons. Okay, so that's always a good way to check your work, to make sure that you have enough electrons in your electron configuration. Now, when I go from beryllium to boron and I add 1 extra electron, well, my 1s and my 2s, we can see that they're filled up, So the next possible place to put my electron, my fifth electron of boron, would be in the 2p. So my electron configuration becomes 1s2, 2s2, 2p1. And like I said earlier, we don't denote our orientation in any way. We just know that it's in one of those orientations. So we just keep it as 2p1. Okay, so our Aufbau principle tells us that we have to fill our energy levels from lowest to highest energy. Our final rule is Hund's rule, which states that the most stable arrangement of electrons is the one in which the number of electrons with the same spin is maximized. So spin being, positive or negative spin, our little up and down arrows, we want to maximize those to be the same. So here we have carbon, which is right after boron. So I now have 1s2, 2s2, 2p2. Carbon has now 6 electrons, so I added one more to my 2p. Now I could have, let's cover this up real quick. I could have added the electron there, okay? But based off of Hund's rule, that would not be maximizing the spin. So in order to maximize the spin, we want as many electrons to have the same spin as possible. So if we look at it this way, we have 3 electrons that are having a positive spin and 3 electrons that have a negative spin. Whereas if I do it the other way, that follows Hund's rule. If I erase what I covered up, I now have 4 electrons with an up spin and 2 electrons with a down spin, meaning that this is the most maximized orientation of those electrons. Those electrons don't want to pair up if they don't have to, okay? And that's also kind of Hund's rule. So let's say electrons will not pair up unless they have to. When I was learning this in chemistry in high school, my teacher made a really nice comment about this, and she said Hund's rule is like when you're getting on a school bus. You each sit in your own seat until there's no more empty seats available, then you have to start pairing up. Electrons do the same thing. So we put electrons into the boxes with the same spin first, and then we only pair up when we don't have any orbitals left that don't have any electrons in them. So electrons will not pair up unless they have to. So let's move on from carbon to nitrogen, and then nitrogen to oxygen to show that. So here we have carbon. Here we have nitrogen. Okay, so we're adding 1 electron. Okay, so that the next electron goes into the last spot of the 2p. So I now have 1, 2, 3, 4, 5 electrons with an up spin, and still only 2 electrons with a down spin. So my up spin, or the same spin, is being maximized. However, our rule also says that electrons will only pair up unless they have to. So when I add 1 more electron to go from nitrogen to oxygen, that 1 electron is going to now follow our Pauli exclusion principle, and it's going to add to our 2p, but instead be in a down spin. Okay, so following Aufbau and also following Pauli exclusion, we still have to fill up our 2p, okay, before we can move on to any other energy level. But so that's Aufbau's principle, that we have to fill up, go lowest to highest energy. The Pauli exclusion principle then tells us that that spin has to be an opposite spin, so we're going to do down spin, which is opposite of our up spin. This is still following Hund's rule because I now have 5 electrons with an up spin and now 3 electrons with a down spin. So I'm still maximizing how many electrons have the same spin. And then we can just look at our electron configurations again. So down here, we're just adding those electrons now to our p orbital. So we have 1s2, 2s2, 2p2 for carbon, and then that P becomes 2p3 in nitrogen, and then for oxygen it becomes 2p4 because we've added additional electrons. And again, because there are 3 orientations of p orbitals, I can fit a maximum of 6 electrons in those p orbitals. So at some point this is going to become 2p6, which we'll see in some of our later examples as well. Okay, so let's do a quick practice on our principles and our rules. What rule or principle is violated in the below diagram? So I have 1s, 2s, and 2p. So right now our electron configuration is looking like 1s, 1, 2s, 1, 2p, 3, because I have 1 electron in my 1s, 1 electron in my 2s, and 3 electrons in my 2p. Okay, so let's think about what principle or rule is being violated. Aufbau, Pauli exclusion, or Hund's rule. Okay, so if we think about our rules, Aufbau says that we have to fill lowest to highest energy. Pauli exclusion says that 2 electrons in the same orbital, or in this case box, can't have the same spin. And Hund's rule tells us that we have to maximize spin. So this is about pairing up. Okay, so let's see. Let's go from the bottom. Maximize spin. Well, all of them have up spins, so that's pretty much maximized. So I'd say this is not a violation of Hund's rule. Okay, Pauli exclusion principle says that 2 electrons that are in the same orbital can't have the same spin. Well, there's no orbital that has 2 electrons, so it's technically not violated because they all have 1 electron in them with 1 spin, so we can tell them apart. Aufbau principle says we have to fill from lowest to highest energy. We know that 1s is our lowest, then we go 2s and 2p. So we didn't fill up our 1s before moving on to our 2s, so we would be violating Aufbau's principle because we didn't fill our boxes before moving on to the next one. So what this should look like is we have 1s, 2s, 2p. We have 1, 2, 3, 4, 5 electrons to work with. So we do 1, 2. Okay, we filled our 1s. We're following Pauli exclusion because they have different spins. So we filled our lowest energy. Now we move on to our next one. So then we have 1, 2, which again, we follow Pauli exclusion by giving them opposite spins. And then my last electron is going to go in my 2p, which is my next highest energy level. So that's what our orbital diagram should have looked like. Okay, so now that we know that what our rules are for writing our electron configuration, we can now use this little diagram here to help us write them for all of our elements, no matter how many electrons they have. Okay, so just a reminder of our general rules. Electrons will reside in the available orbitals of the lowest possible energy. So here in our diagram that you have on in your packet and in your test taking resources, this is lowest energy, and this is highest energy. Okay, each orbital can accommodate a maximum of 2 electrons. So each box that we have has 2 electrons in it. Electrons will not pair in orbitals if an empty orbital is available. Okay, and that's only in things like 2p and 3d, where we have multiples at the same energy level. And orbitals will fill in the order indicated in this figure. So we're going to use this figure a lot to start writing our electron configurations. And what we have to do is start following the arrows. So we start with 1s. Then when we're done with 1s, we go to 2s, which is what we saw in all of our configurations. Once we're done with 2s, we go to 2p, and then we go to 3s. Once we're done with 3s, we go to 3p, and so on and so on. So you follow the arrows as you go, and they kind of come back up once you finished one arrow. Okay, so that's what they mean by follow the order indicated in the figure. So let's do one example together where we use this diagram to write our electron configuration. So we have calcium, which has 20 electrons. So 20 electrons that we need to organize into specific orbitals. So we start here, we have 1s, okay, and we know that the s orbital can hold 2 electrons. Actually, I'm going to do this a different way. We're going to draw our orbital diagram first. So 1s, we have 2 electrons. So then we go to 2s, which is next, which is another single box. Okay, so that's 2s, that's 4 electrons total. We have 16 electrons left. Once I'm done with the 2s, we go up to our next row and we do 2p. So 2p is our 6, we have 3 boxes that show our 2p. So we're going to do 1, 2, 3, 4, 5, 6. So note how I've added my electrons in following Hund's rule, where I put them without being paired up until they have to. That'll be very important for when you have we don't have completely full shells, when we don't have completely full orbitals. Okay, so you always want to follow those rules even when you're filling in. So next up we have 3s, and let's just take count of how many electrons we've used. We've used 2, 4, and then this is what, 6. So we've used 10 electrons so far. Okay, so my 3s is going to be 2 electrons. Okay, so that's now 12 electrons. I now move up to my next row. I go through my 2p, or my 3p, sorry, my 3p, which again has 3 boxes in it. And we do 1, 2, 3, 4, 5, 6. Let's take stock. That's what, 6, 12, 14, 16, 18 electrons. So that's my 3p. So I need 2 more electrons, and we come up to our 4s next, which holds 2 electrons. So that's a total of 20 electrons. So that's the orbital diagram for calcium. Now we can take that orbital diagram and turn it into an electron configuration. So we have 1s, there's 2 electrons in that one. 2s, there's 2 electrons in the 2s. 2p, there's 6 electrons in the 2p orientation. So remember, we have 3 orientations of p. Each can have 2 electrons. So in total, the p orbitals overall can house 6 electrons. So we put our superscript as a 6. We then have our 3s, and that has 2 electrons. We have our 3p, which again is filled with 6 electrons. And we have our 4s, which has 2 electrons. So we've written our orbital diagram, as well as our electron configuration. Now I drew my orbital diagram linearly, mainly because drawing them with specific energies or going up in energy can be, there may not be enough room, but on your ALEKS homework you may be asked to draw them at their specific energy levels, which ALEKS will give you the lines to do that, so just keep that in mind. But a linear orbital diagram like this one is perfectly fine because you're showing the energy from lowest on the left to highest on the right. Okay, let's do a few more examples. Now, with electron configurations, it really just comes down to practicing and following this diagram, because you'll then start to learn kind of the overall pattern of the electron configuration, because electrons, what we're counting here, are literally just counting numbers, 1, 2, 3, 4, 5, so on. So it really is kind of just truncated by how many electrons you have. So you'll notice a lot of similarities. We're going to start with 1s, then we're going to go to 2s, then 2p, because they're following this diagram. So you're going to notice that a lot of these they start off very similarly. So the first thing we want to do is, with lithium, we want to figure out how many electrons it has. Okay, so lithium has 3 electrons. We get that from the periodic table. So I have 3 electrons that I need to put into my electron configuration and my orbital diagram. I personally find it easier, as you're learning, to draw out the orbital diagram and then write the electron configuration, because you're physically seeing where the electrons are going. So let's start with the orbital diagram. We're going to start with our 1s. We're going to go through here. 1s, that has 2 electrons. Okay. And then we go into our 2s. And that can hold 2 more electrons, but I only have 1 electron to utilize. And that's 3 electrons total. So lithium only has 3 electrons. So those electrons are organized with 1s, 2, 2s, 1. There's 2 electrons in the 1s orbital, in the lowest energy orbital, and there's 1 electron in the 2s orbital, the higher energy level. Okay, we've seen that one before, so let's move on to fluorine. Fluorine, if we look on our periodic table, has 9 electrons. Okay, so let's start drawing. Get rid of our lines here. Let's start drawing our orbital diagram. We're going to start with the 1s, because that's where our diagram tells us to go. So that's 2 electrons. We then have our 2s, that's another 2 electrons, so I've used 4 electrons so far. Okay, so that was my next one, my 2s. So after 2s, I go up and I use 2p, which has 3 boxes. Okay, so I have 4 electrons. I've used 4 electrons. I have 5 electrons left. So I do 1, 2, 3, 4, 5. So here's a case where we don't have enough electrons to fill our p orbital or our s orbital or whatever. We have an unfilled orbital, which is totally fine. There's not enough electrons to go around. So we just leave it as is. And this is why following Hund's rule is very important, because we want to show that we first maximized our spin before we paired them up. Okay. So our electron configuration then becomes 1s, 2, 2s, 2, 2p, 1, 2, 3, 4, 5. And again, if we add up our superscripts, 5 plus 2 plus 2 equals 9. 9 electrons in fluorine. Okay. Let's try one that's a little bit more difficult. Rubidium. Let's find rubidium on our periodic table. And let's see, how many electrons does rubidium have? Let's see, it has 37 electrons. Whoa, this one's gonna need a lot of space for this one. 37 electrons that we have to put into these boxes. So we're gonna use our chart, because our chart is gonna tell us the order that we have to fill them in. So we're going to start with our orbital diagram. 1s, we know that there's 2 electrons there. 2s, there's 2 electrons there. Now, so we've done 1s, 2s, now we do our 2p. Oops, I made that far too large. 2p, 1, 2, 3, 4, 5, 6. So I've used 10 electrons as of right now, so I have 27 left to go. After 2p, I go into my 3s. That holds another 2 electrons. I go into my 3p next. One, two, three, four, five, 6. And after 3p, we go to 4s. And that has 2 electrons. Here's where I oftentimes see students run into issues. After 4s, our next spot is the 3d. Now, students get confused by this because 3 is lower in number than it is 4. But if you remember back to our slide where we talked about different energy levels, when we have multi-electron atoms, we said that the energy levels start to change and how the 4s was more energetically favorable than the 3d. This is where it's coming out because we have to fill our electrons from lowest to highest energy. 4s is lower in energy than the 5 orientations of 3d, which is why it comes first. And that's what our diagram here tells us as well. So as long as you're following this diagram, okay, you will not put anything in the wrong spot. So just follow the diagram as is. So with 3D, there are 5 orientations, so I need to draw 5 boxes. Okay, so 5 boxes. There's my 3D. So we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's just see, how many electrons do we use? Well, that's 10. So that's 2 plus 2 plus 6 is 10. Then we have 2 plus 6, that's 18. That's 2, that's 20. And 3D has 10, so that's 30. So I now have 7 electrons left to do my orbital diagram. So after 3D, we have 4p, so that's 3 boxes. 4p, 1, 2, 3, 4, 5, 6. Okay, so that's another 6 electrons. So I only have 1 electron left, and that 1 electron is going to go in my 5s orbital. And it's just going to be by itself there, because there's no more electrons to put in there. So it's okay to have unpaired electrons if you don't have enough electrons left. Those unpaired electrons, as we can see, should be in our very last orbital of our orbital diagram. You don't want to have unpaired electrons in one of these random orbitals down here, because then you would be not following all of our rules where we say we have to go from lowest to highest energy, pair up only when we have to, and stuff like that. So we got to follow those rules, and what those rules will tell us is that all of these unpaired electrons should be in the very end. Okay, so now that we have our orbital diagram, we can use that to draw our electron configuration. So in my 1s orbital, I have 2 electrons. In my 2s orbital, I have 2 electrons. In my 2p orbital, I have 6 electrons. In my 3s orbital, I have 2 electrons. In my 3p orbital, I have 6 electrons. In my 4s, I have 2 electrons. In my 3d, I have 10 electrons. In my 4p, I have 6 electrons. And in my 5s, I only have 1 electron. So my electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. Okay, so when we went from 3D, we jumped back over into the 4p's because 4p is now higher in energy than 3D, and then we go into our 5s. So we have to remember to follow this diagram whenever we are doing our electron configurations, so we don't get caught up in numbering incorrectly when we go between 4 and 3, as well as when we go from 4 and 5, when we get into the next d orbitals and stuff like that. So it happens all the time. It happens throughout here. We go 4s or 5s, then we come up here, and now we're in the 4d. Then we go 5p, 6s, 4f, 5d. So they're offset, and we'll talk about why here in a second. Okay, so what I want you to do is I want you to pause the video, and I want you to try some of these on your own. So we're going to look up on the periodic table how many electrons each of these has. we're then going to utilize our diagram to write out our orbital diagrams to then write our electron configuration. And my last question here is to indicate how many unpaired electrons the atom has. How many unpaired electrons does this atom have? So take a second, pause the video, and try these on your own. We'll come back together here in a second to work on them together. Okay, phosphorus I have as having 15 electrons because it is element number 15. Don't confuse phosphorus with potassium. Okay, potassium is K and it has 19 electrons. This is phosphorus P with 15 electrons. Now, what I'm going to do is I'm going to just write the electron configuration, not the orbital diagram, for each of these, just so you can see how to use this diagram without having to draw the orbital diagram. If that makes you comfortable, if that's the way that you're seeing it as you learn it, then please feel free to do that. But you should also get comfortable with not drawing the orbital diagram and being able to use this diagram here to just write out the electron configuration. You should be comfortable with either way. So for this one, I'm just going to draw the electron configuration or write it out without drawing the orbital diagram at the same time. Okay, so we start off with 1s, and I know that can hold 2 electrons. We then jump up to our 2s, which again can hold 2 electrons. After 2s, we go to 2p, which we know can hold 6 electrons maximum. And after 2p, we go to 3s, which can hold 2 electrons. I'm just going to take a second to pause and make sure I haven't used too many electrons. So I have 2, 4, 10 electrons, 12 electrons total. I have 3 electrons left, so let's see where those 3 electrons are going to be. Well, they're going to next go into the 3p, and I only have 3 electrons to give away. So that's not going to be a full 3p6 because there's not enough electrons. If you put 3p6, if you added those up, you would have 18 electrons, which is too many. Okay, so remember, always double check your own work and show that you have the same number of electrons in your electron configuration as you do the element. So this equals 15 electrons. Okay, so my next question was how many unpaired electrons are in the atom? Well, if we look at an orbital diagram for 3p, if I have 1, 2, 3 electrons, I'm going to put them into their individual boxes before I start pairing them up. Since there's only 3 electrons, I put 1 electron in each box, meaning I have 3 unpaired electrons. So each of these electrons are in their individual orbitals, not paired up yet, so they're unpaired. Okay, let's try the next one. Nickel. Nickel I have as having 28 electrons. It is element number 28. So again, let me just erase my lines here so we can still see. We're going to follow our diagram. We start off with 1s. We know that can hold 2. After 1s, we jump into 2s, which again holds 2. Once we go there, we go to 2p. That holds 6 electrons. After 2p, we hit 3s. That holds 2 electrons. We jump into 3p, which holds 6 electrons. And then we jump into 4s, which holds 2. So let's count our electrons. We have 2, 4, 10, 12, 18, 20, so I have 8 electrons to go. My next orbital after the 4s is our 3d, so again, we're just following our diagram. We know that the 3d is higher in energy than the 4s, so it's going to come after the 4s. So 3d, well, we know d orbitals can hold a maximum of 10 electrons. I only have 8 electrons to give away, so those 8 electrons are going to go in my d orbital. So to look at our unpaired electrons, well, d orbital has 5 orientations. So we have 1, 2, 3, 4, 5, 6, 7, 8. We filled those based off of Hund's rule, and because of that, I have 2 unpaired electrons. Okay, carbon next. Carbon has 6 electrons. Okay, so we're going to follow our lines again. So we start with 1s. 1s has 2. Then we jump to our 2s. That has 2. Then we jump to our 2p. We know that has 6. But if I take stock, I have too many electrons. I have 10 electrons there, and I only had 6 electrons to give away. So we're going to erase that. Let's see, I have 2, 4, so I have 2 electrons left. I add those up, that's 6 electrons. So if I look at my 2p diagram, I have 1, 2, meaning I have 2 unpaired electrons. So sometimes we just don't have filled shells, and that's because there's not enough electrons to fill them, which is totally fine. That's how we differentiate all of our different elements. Okay, argon. Let's do argon next. Argon has 18 electrons. Okay, so let's follow our plot. We have 1s, 2, we jump over to 2s, 2, we then go to 2p6, that's 10 electrons, I have 8 left, 3s, 2, and now we're into 3p6, so let's count, 2, 4, 10, 12, 18, that's 18 electrons. If we look at our 3p orbital, 1, 2, 3, 4, 5, 6, we have no unpaired electrons. Okay, so hopefully you're starting to see that with each one of these, if something has more electrons, so let's look at phosphorus and nickel, we're starting off all in the same. So 1s2, 2s2, 2p6, 3s2, blah, blah, blah. If it has more than those electrons, well, you just keep on going. Okay, so I only have 6 electrons in carbon, so it's 1s2, which starts off everything else is 1s2, then we go to 2s2, then we just stop in the 2p. So it's getting very repetitive, and all you have to do is just stop at the point that you've used up all of your electrons. And if you ever forget your order, you just follow the diagram. Okay, so writing all of those electron configurations, especially for ones like rubidium and argon and stuff like that, can get a little bit taxing because there's a lot of electrons to show in an orbital diagram and an electron configuration. So the electron configurations of all elements, except for hydrogen and helium, can be represented using a noble gas core. Okay, so what I want to do to illustrate this is to write the electron configuration for both potassium and argon, which we just did. So we did argon as 1s2, 2s2, 2p6, 3s2, 3p6, so that's our 18 electrons. So let's try potassium. Well, potassium has 19 electrons, so it's going to start off very similar to argon. 1s2, 2s2, 2p6, 3s2, 3p6, so that's 18 electrons. We now have 1 electron to give away, so that's going to go in the 4s if we follow our diagram, and that 1 electron is going to go there. So if we compare our answers, everything up through 3p6 is the exact same between argon and potassium because they have 18 electrons in common. Okay, so they have 18 electrons in common. What the noble gas core is saying is, well, argon is a noble gas, so we could say that this section is really close to argon, right? It's the exact same as argon. It only differs from argon by what comes after those 18 electrons. So the noble gas core is a way of simplifying our electron configuration for all of our elements so that we don't have to show every single electron, because the noble gases have electrons in common with all of our elements. So the electron configurations are shown here. So this is exactly what we just showed. So because the electron configuration going up through 3p6 is the same, we can simplify our potassium expression to say, well, the first few, oops, I thought that was a highlighter. The first portion here is made up of electrons that are from argon. The only difference is here, so we can simplify by saying, well, we're going to put argon in brackets, and everything that's different from argon comes after those brackets. So whatever closest noble gas to our element on a periodic table is going to be our noble gas core. That's the maximum number of electrons that our element has in common with that noble gas. Okay, so if you look on your periodic table, the noble gas that comes before potassium is argon. So I should say comes before our element. Okay, so let's do some practice problems here. So we want to write the electron configuration for arsenic, which has 33 electrons in its ground state, meaning that they're all going to be, we're just going to follow these. When it says in the ground state, just means nothing, okay? We can basically ignore that because we're not moving any of those electrons into a higher lying excited state or any of those higher states. So that's just what it's saying. So the setup for this problem, well, if we look at where arsenic is on our periodic table, the noble gas that comes before it is argon. So of the 33 electrons that arsenic has, 18 of those electrons are similar to arsenic or argon. So our noble gas core is going to be Ar. Okay, so then we're going to find 15 electrons that differ between argon and arsenic. So we then follow our diagram for those 15 electrons. And we're not starting here because argon ended at 3p. So we've already done this portion of our diagram. So our next portion that we have to do for our 15 electrons is now starting with 4s, which has 2. Then we jump into the 3d, which has 10, so that's 12 of our electrons left. And then we finally go to 4p. So we've used 12, we have 3 electrons left for arsenic. So that is our noble gas configuration of arsenic using argon as our noble gas. What we can't do is say, well, krypton is really close to it. It's not like we can say Kr minus 3 electrons. We can't do that. So it has to be the noble gas that comes before it. It's before arsenic. Okay, so let's continue to practice that with electrons coming before the noble gas that comes before it. So if we're looking at sulfur, we want to do the noble gas core configuration for sulfur. Well, sulfur is right here. So the noble gas that comes before it, well, I'm going to work backwards from my periodic table, okay, which leads me to neon. So we have neon, Okay, neon has 10 electrons, sulfur has 16 electrons, so we have 6 electrons that we have to fill in. If we look at our chart, neon ends in the 2p, so our next stop on our plot, on our diagram, is the 3s, right? 3s comes after 2p. So we have 3s2, and then we have 3p, which comes next. We have 1, 2, 3, 4 electrons of sulfur left over. Okay, now what you could do, if this is confusing for you, is you can write out the full electron configuration for sulfur, and then cut off where those 10 electrons come from neon. So you could write it as 1s2, 2s2, 2p6, 3s2, 3p4. You could then say, okay, I know neon has 10 electrons, so that's 2, 4, 10. So that's 10 electrons. So you write those as neon, and then 3s2, 3p4. Okay, however way you want to write it. Writing it out this way, the extended way, is kind of not the purpose of the Noble Gas Core, because it's meant to simplify, so you don't have to write all of those out. But as you're learning this and as you're getting the hang of this and starting to see the trends and kind of what happens over and over, the periodicity of it all, hopefully that'll then start to show you how to do it without having to draw out the entire electron configuration. Okay, so let's try another one. Let's do antimony. Antimony has one of those funny element symbols. Antimony is SB. SB is down here. Okay, so the noble gas, the noble gas that comes before antimony, we're going to work backwards. I'm going to go up to 4, is krypton. Kr. Krypton has how many electrons? 36 electrons. Antimony has 51 electrons, so we need to get up to 15 extra electrons after Kr. Okay, so krypton ends in the 4p orbital. Again, if you wanted to write out the full electron configuration for antimony and then cut off at the 36th electron and show that as krypton, you're more than welcome to do that. So krypton then comes after that is 5s2. If we then follow our diagram, 4d10 comes after 5s2. And then after 4d10 we have 5p, but I don't have enough electrons. There's only 3 electrons left, so they will go in my p orbital. Okay. If it feels like I'm going a little too fast, feel free to pause the video, write out the full electron configurations for each of these elements, find the overlapping electrons with the noble gases, cut those out, and put them in as in their little brackets so that it's easy for you to see it. Okay, so just like we did for sulfur. Okay, let's try one more. So we have iron. Iron is Fe. Fe is right here on our periodic table. So if we work backwards, we're going to have a noble gas core of argon again, Ar, which has 18 electrons, and iron has 26, so we need another 8 electrons to add on to it. So we know that argon ends at 3p, so we're going to go, next is our 4s, which has 2. Again, we're following our diagram. So next up after 3p is 4s, and after 4s is our 3d. Now I only had 8 electrons, I've already used 2, so my last 6 electrons are going to be in the 3d orbital for iron. Okay, so again, we can write this out as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, and we can say, okay, argon has 18 electrons, that's 18 electrons right there. So these are argon. We ignore those and say everything else that comes after it is for iron. 4s2, 3d6. Okay. Before we move on, I just want to reiterate that these electron configurations, they do just take practice, following the diagram, following our rules, writing out your orbital diagrams, using those to write your electron configurations. Those are all how we learn. Okay, so doing those step by step will help you learn to hopefully get to the point where you know the order 1s2, 2s2, 2p6, 3s2, so on and so on. You'll start getting into your head, okay, that you won't even need the orbital diagram to then write the configuration. Then, after you know the configuration, you won't even need to write the whole one out to write the noble gas configuration. Okay, so just keep practicing them. If you need more practice, just pull out your periodic table and just pick a random element and write out its electron configuration. That's always useful. And also, start working on your ALEKS homework, because they have a lot of practice in there for you as well. And you can always redo problems with no effect to your grade. Okay, you can always use your unlimited temps to get more and more practice. It's all about practice. Okay, so the electrons that are occupying the outermost shell or the outermost orbitals are called valence electrons. Valence electrons are the ones in our outermost orbitals. Those electrons are found in the orbitals with the highest n value. Okay, so we typically show this. They're going to be the ones that come after that noble gas core in our noble gas configuration. So here I have one for sodium. Sodium has 11 electrons, so 1s2, 2s2, 2p6, 3s1. Its noble gas core is neon, so neon 3s1. Sodium then has one valence electron because the highest n is 3. That's our highest n value. That's like our outermost shell. So here's our nucleus again. There's n equals 1, n equals 2, n equals 3. So in sodium, we have electrons here, and then we have one electron out there. There's only one electron in our outermost shell, so that is our valence electron. It is the electron in the n shell that is of the highest number. So n in this case was 3, that's our highest n. There's one electron, so there's one valence electron. The non-valence electrons, the electrons that are not in that highest n value, those are called our core electrons and are electrons that match the noble gas. Okay, so our core electrons in sodium are 1s2, 2s2, 2p6, so that's 10 core electrons. Neon also has 10 electrons. Okay, so anything that comes after the noble gas would be considered valence. There's one stipulation to that we'll talk about here in a second. So anything that comes after that noble gas is our valence electron. Our core electrons are then the ones that match that noble gas. We can group the elements according to the type of subshell that their valence electrons exist in. And we refer to these as blocks on the periodic table. So if you look through all of our previous electron configurations that we've written so far, you've noticed that where we've ended kind of is in different types of orbitals depending on where we're at on the periodic table. Maybe we left off with unpaired electrons in the S or the P or the D. Okay, so that's what we're referring to as being able to group them based on where their valence electrons are. So we have the S block. I'm going to try to highlight these. So the S block is right here. So that's for groups 1 and 2. Okay, their valence electrons are in the s orbital. So if you look at what we did for sodium, we did lithium, we did magnesium and potassium. Okay, we ended up with our last electrons being in the s orbitals. We then have the p block, okay, which is over here. The other side of our periodic table. And this is for groups 3A through 8A, or 13 through 18. Okay, their valence electrons end up in a p orbital. Next, we have our D block. Okay, this is our transition metals. Okay, so we'll write this as our transition metals. So what we just did with iron, its last electrons, those unpaired electrons, those last electrons that we had, they ended up in the d orbital. So that's our D block. Transition metals have their valence electrons in the d orbitals. And finally, we have the F block, where their valence electrons are in the f orbitals. So that's our lanthanides and our actinides, if you remember our grouping names from our previous lessons. Okay, so it's also really useful as you're going through and utilizing your own periodic table and writing these electron configurations, because if you have an atom that's in the p block, you know that its valence electrons, its last electrons, should be in a p orbital, and if they're not, well, then you did something wrong and you should redo it. Okay, so it's a good way to kind of help yourself orient yourself on the periodic table as to where those last electrons should be. Also, because we have, if you look at our periodic table here, it's labeled 1s, 2s, 2p. This version of the periodic table follows that list, that diagram that we have to follow, because you can start reading the periodic table and its electron configurations from left to right. So you have 1s. Once you're done with 1s, you jump down and you do 2s. After 2s, you have 2p. Once you're done with 2p, you do 3s, which is just like our diagram. Then we have 3p. And then we have 4s. And then that's where we jump into the 3d, like our weird rule says. So you go 3d, and then 4p, and so on and so forth. So if you start reading the periodic table from left to right, you don't even need that diagram anymore, because the periodic table tells you the order that the electron configuration should be in, as long as you remember that at the transition metals, okay, your values start to change with your d orbitals. They go down by 1. Okay, so again, you're more than welcome to use that orbital diagram, or that diagram that I gave you previously, that is available to you on all of your tests, so you can always use that, but your periodic table is equally as useful. Okay, so to go along with that, there is a distinct pattern to the electron configurations of the elements in a particular group, because they all have the same number of valence electrons. So all of the elements in group 1 have 1 valence electron, and we can see that by their electron configurations. Yes, they vary in their noble gas, but their last electrons, their valence electrons, are all in the s, and they all have 1. So group 1, group 1a, has 1 valence electron. Then when we get to group 2, or group 2a, they have 2 valence electrons, which we can see by having 2s2, 3s2, 4s2, everything like that. They all have the same number of valence electrons, 2. So our group numbers tell us how many valence electrons we have. So all elements that are in the p block are going to have their valence electrons in both s and p orbitals. Okay, so if we look at phosphorus, its valence electrons are in 3s2 and 3p3. Okay, so it has a total of 5 valence electrons. Okay, now D block elements, or our transition metals, are a little bit trickier, okay, because that's where we start to see the difference in our N values. So all the D block metals, or D block elements, the transition metals, have their valence electrons in both being the important word there, the s and the d orbitals. So if we look at vanadium, we have argon 4s2 3d3. Okay, its valence electrons are in the 4s and the 3d. So it also has a total of 5 valence electrons. Okay, now this is an exception, so we're going to point this up there. This is an exception to that highest N rule because your N of 3 and your N of 4 shells are not totally filled with electrons yet, so they are all considered valence electrons in both the 4s and the 3d. And then, further on it could be the 5s and the 4d and everything like that. So for our d block elements, they exist in both the s and the d orbitals. Okay, so again, we can use our group numbers like we did for group 1 and 2 to tell us how many valence electrons we have. So for our S and our D blocks, our group number is equal to our valence electrons. So group 1 has 1 valence electron, group 2 has 2 valence electrons, group 3 has 3 valence, or 3b has 3, 4, 5, there's vanadium, which we just said has 5, and so on and so forth. Okay, all of our group numbers that we have here tell us our number of valence electrons. So if I said, what is, palladium, PD, palladium, how many valence electrons does it have? Well, it's in group 10, so it has 10 valence electrons. For the p block elements, there's 2 ways to tell how many valence electrons it has, and it depends on which notation you're looking at on your periodic table. So if you're looking at the teens, so 13, 14, 15, 16, 17, and 18, take that number and subtract out 10, and that tells you how many valence electrons it has. So oxygen is in group 16. 16 minus 10 is 6 valence electrons. Okay, you have to do the subtraction by 10 because if you look at oxygen, it has 6 valence electrons. It doesn't have 16, can have 16 valence electrons because there's only 8 electrons for it to have. Okay, so oxygen has 6 valence electrons. Another way you can look at it is if you look at the A notation, 3A, 4A, 5A, 6A, 7A, and 8A. If you just look at that group number with the A on it, tells you how many valence electrons it is because they differ just by 10. So boron has 3 valence, nitrogen has 5 valence. Okay, so you can look at it either way. So I have the example here of selenium. Selenium is number 34. It's right here. How many valence electrons does it have? Well, it's in group 16, so I would do 16 minus 10, 6 valence. Or I can look and see that it's in group 6A. That's 6 valence electrons. Okay, so you can look at it either way. Let's see. Okay, so we did, these were the 3 examples we did before with our noble gas configurations. Let's figure out how many valence electrons each of these have. And feel free to look at your own periodic table and look at the group numbers to show that it corresponds to the same thing. So sulfur, that's a p block element. We see it in the p block. So its valence electrons are in both the s and the p orbitals. So we could just add up the electrons from s and p. That's 6 valence electrons. It's also in group 16. So we do 16 minus 10, 6 valence. It's also in group 6A. Oops. So that's 6 valence. There's many ways to tell this, okay? So if you can't remember one way, try to remember the other. Let's see. So then we have antimony. Antimony is number 51. It's a p block element, so its valence electrons are only in the s and the p orbitals, so we ignore that d. Goodbye. That's the whole reason we have to subtract by 10 anyways. It's because of those 10 d orbitals, d electrons. Okay, so it's only in the s and the p, so we add those up, and that's 5 valence electrons in antimony. Antimony is in group 15. We subtract off those 10 electrons and we get 5 valence. It's also in group 5A, so that's 5 valence. Finally, we have iron. Iron is a D block element, so it's a transition metal, and transition metals have their valence electrons in the s and the d orbitals. So we look at s and d, we add those up, and we get 8 valence electrons. It's also in group 8 or 8b, so that would be 8 valence electrons. Okay, there are a couple exceptions, because what's chemistry without a few exceptions? If we haven't learned that from the beginning of the semester, well, we got to start learning it now, okay? Everything has an exception. There are a few exceptions to our electron configurations, specifically in chromium and in copper. Now, chromium has, 24 electrons, and its electron configuration is represented as argon 4s1 3d5. So if we look at that, so we have 4s1 3d5. Okay. Now this is different than what our typical rules of electron configurations would be, where we have 4s2 3d4. Okay, so the blue is the way that the accepted orbital diagram and configuration, and the red is the not expected one. And this is because of two things. First, because of Hund's rule, because what's happening, I'm going to zoom in here, is we want to maximize spin. Okay, so we have this one electron, we have 5 electrons of upspin and 1 electron of downspin. So what's going to happen is chromium says, well, I could maximize my spin by moving it up here and getting rid of that. That way, which is up here, I have 6 electrons all with upspin and no electrons with downspin. Okay, so we're first maximizing spin. The other reason is because orbitals like to be half filled or completely filled, if that's possible. Now, it's not like all of the electrons are going to rearrange so that there's completely filled orbitals and half-filled orbitals or anything like that. This only happens with only a certain number of elements on the periodic table, specifically chromium and copper. Okay, so what's happening here is the S, so I'm going to look at my accepted one. The S only has 2 options. It's either filled with 2 or half filled with 1. So it's a 50-50. It's either one or the other, half filled or whole filled. Prior to me moving this electron, oops, that was a bad idea. Prior to me moving this electron, okay, never moved that, goodbye. The d orbital was 1 electron away from being half filled. So basically what's happening is the S is saying, well, I'm fine with being half filled with 1 electron if it means you can be half filled and I give you that 1 electron to be half filled. So it's just a more energetically favorable position for the element to be in, to have 2 half-filled shells instead of 1 whole-filled shell and 1 almost half-filled shell. It's just more energetically favorable that way. Okay, so this happens for chromium. So this was our example for chromium. It also happens for copper for the same way. So here's the diagram for copper. The electron, this electron here, was originally down here in the 4s, but copper was 1 electron away from being a whole-filled D shell, so S is like, well, I'll be half-filled if it means you can be whole-filled. It's fine doing that. It's equally as energetically favorable. So it's just a rearrangement of these electrons so that these orbitals can be in a more energetically favored state. Now, I want to point out that this only happens between the S and D orbitals in chromium, copper, molybdenum, and silver. Oops. Molybdenum MO and silver AG. It does not happen anywhere else on the periodic table. It's very important. It's not like an s orbital or an s electron is going to move up to a p orbital. They're too far apart in energy. This only happens because, if you remember, when we started to mix those energy levels between s and d, okay, we went from 4s to 3d, they're very close in energy. So those energy levels are close enough that they can exchange these electrons to be more energetically favorable. It only happens between the s and the d. It does not happen anywhere else. No other electrons will do this. No other orbitals will do this. Just s and d orbitals, and only for specifically chromium, copper, molybdenum, and silver. That is it. Nowhere else. So you just have to remember those four. It's not happening anywhere else. Okay. So let's practice. Let's look at some of these electron configurations, and let's determine the symbol for the element. These are all ground state configurations, meaning we can just ignore the fact that it says ground state because it's just going to tell us where all those electrons are. There's no extra energy or anything like that. So our first one is argon, 4s2, 3d10, 4p1. Now there's many ways you can go about figuring this out. You can look at the valence shells, like valence electrons. You can count up the total number of electrons. You can go from the noble gas and count however many electrons there are after that. You can do it many different ways. So you can start off by saying, well, argon has 18 electrons. So 18 plus 12 is 30, and then plus one more is 31 electrons. So 31 electrons is gallium. Okay. You can also say, well, its last electron is in a p orbital, so we know it's in the p shell, or p block, I should say. It's in the p block. And because p block elements have their valence electrons in the s and p, it has 3 valence electrons. 3 valence electrons. Okay, and because that last electron comes in the 4 shell, we're going to be in row 4. So row 4, group 3, because there's 3 valence electrons, is then gallium. You could do that as well. Or you could start with argon, and you know that there's, 13 electrons after that, so you go argon. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You could do it many different ways. Okay, so let's see. Let me erase all of this. Get rid of that. So we can do our next one. What's our next one? Oh, come on. Why are we doing this? Erase. Goodbye. Okay, there we go. So we have krypton, 5s2, 4d1. So its valence electrons are in 4d. So we have what? 3 valence electrons. Okay, so we know we're going to be somewhere here. We know we go from krypton, so we start at krypton, and we have 3 electrons to give away. 1, 2, 3. So it puts me at Y for yttrium. This one wasn't gallium. Okay, Y for yttrium. Okay, so that's our next one. You could also say krypton has 36 plus 3 is 39. Element 39 is yttrium. Okay, and our last one is argon, 4s1, 3d5. Ooh, that's one of our exceptions because we have a half-filled S and a half-filled D. Okay, so we have to identify those. So since that S does not have a 2, it has a 1, but then we moved on, that means it's an exception. So this is one of our exceptions. So we know it's either going to be chromium or molybdenum or copper and silver. So we're at argon. I have 6 electrons after that, so it's 1, 2, 3, 4, 5, 6. So this is chromium. We could also say that this has 6 valence electrons, and it is in group 6. Okay. So there's many ways to figure it out. However way makes sense to you, do it that way. Okay, let's do some more practice. Without using your periodic table, write the electron configuration of these random elements with the following atomic numbers. So we have 10 electrons, 22 electrons, and 35 electrons. So we can start off using our diagram. 1s has 2. Then we jump up to 2s2. We then go to 2p6, and that uses up all of our elements. And if you cared to look at your periodic table to then see what element this is, this would be neon. Okay, now what I want you to do is pause the video and try these last two problems on this slide for 22 electrons and 35 electrons. Okay, 22 electron puts us at 1s2, 2s2, 2p6, that's 10 electrons. So we have 12 to give away. 3s2, 3p6, 4s2, 3d2. So I just followed my diagram until I ran out of electrons. My last one is 35 electrons, so I know I'm going to have the same as at least up to there. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now I have 3d10. Okay, so that leaves me with, that's 30 electrons. I have 5 electrons left, so it's going to go for p5. I'm missing 1 electron, but that's okay. I don't have any more electrons to give away. Okay, so take a second, look those over, double check your own answers against those. If you weren't correct, if you had one wrong or something like that, just make sure you're following this diagram. Okay, and again, it just takes practice. Practice, practice, practice. Okay, and our last practice problem for this lesson is to specify the group on the periodic table in which each of the following elements is found. So we have to look at their valence electrons. Okay, so pull out your own periodic table so that you can look up where these group numbers come from. So we have argon 4s1. So if it's s1, that means there's only one valence electron because the core electrons come from argon. So one valence electron. This puts us in group 1. Next up we have argon 4s2, 3d10, 4p3. Okay, so if our last electrons come in the p orbitals, this means we're a p block element. So our valence electrons come from the p and the s orbitals because they have the same n value. So we have 5 valence electrons. So this comes from group 5a or group 15. You try the last problem on your own, and I'll write the answer here in a second. Did you get group 8 or group 8b? Because it is a transition element. Our last electrons are in a d orbital, so this is a d block element or a transition metal. So there's 8 electrons. So group 8 or group 8b. Okay, so that ends our lesson on electron configurations of our elements. Please practice these. Utilize your ALEKS homework to start practicing these before you move on to our next lesson, where we're going to then be writing electron configurations of ions, which takes the electron configurations of our neutral elements and changes them. So we can't do that until we have a good foundation on this point first. So practice these, master these before you move on.